So, there are two broad approaches. So far the fuzzy logic controller design is concerned. One approach is Mamdani approach and another is Takagi-Sugeno approach. Two approaches are different the way they treated the fuzzy logic controller design. We have discussed the Mamdani approach and we see that the Mamdani approach follows a rule base and then fuzzy linguistic state and then fuzzification of the input and then produce the fuzzy output and then crisp value. The method more or less same there in the Takagi-Sugeno approach, but the way they treat the fuzzy inference engine is different. Now, fuzzy inference engine rather more what is called the interpretable. So far the Mamdani approach is concerned. However, in case of Takagi-Sugeno approach, it is less interpretable. So, interpretation means anybody can see from the design how it works, but Takagi-Sugeno approach is bit difficult because it follows certain mathematical treatment. So far the inference engine is concerned. Now, so far the output quality is concerned, the Mamdani approach is less accurate, whereas Takagi-Sugeno give more accurate output. And output calculation, if we consider according to the two different approaches, Mamdani approach follows the standard fuzzification method. So, fuzzification method if we follow COG, it is computationally expensive, whereas the Takagi-Sugeno approach follow the simple numerical calculation and it is faster. So, we can broadly can say that Mamdani approach is easy to interpret, but less accurate and computationally bit expensive. On the other hand, Takagi-Sugeno approach is difficult to interpret, accurate, more accurate than the Mamdani approach, and then calculation is fast. So, if you want to design a fast and accurate fuzzy logic controller, then we can follow Takagi-Sugeno approach. But there is one issue, Takagi-Sugeno approach as it needs some mathematical treatment. So, whatever the rules are there, they needs to be stored in the form of some mathematical representation, and that is a big challenge for the designer. So, if the designer is not so much experienced, then they can follow certain difficulties in this direction, whereas Mamdani approach is very easy to frame the rules and then rule base and then inference engine. So, these are the two differences are there. Obviously, there is a trade off. Now, let us see how the Takagi-Sugeno approach, so far the fuzzy logic controller is concerned, and then how it works. So, we will consider one example, so that we can understand the Takagi-Sugeno approach, and mainly in terms of input example case studies, rather we will explain the step, whatever the methods and technologies are there, I will discuss in time. Anyway, let us proceed here the Takagi-Sugeno approach. Now, according to this approach, every rule is represented as it is in the same as Mamdani approach using the if then clause. Now, for a system, if there are n input, then a rule in the Takagi-Sugeno approach takes this form. It is the rule that is with the n input x 1, x 2 and x n. So, if n input at any instant having its own value, and if these are the input which basically related to the fuzzy state A 1, these are input fuzzy state A 2 and these are nth input the fuzzy state A n, then the rule will take this form. Now, this is the rule, and if this is the rule, then the output of the rule also can be expressed mathematically, and then for this input the output is shown here. So, it is basically input x 1, x 2, x n and a 0, a 1, a 2 and a n are the coefficients. Now, how these coefficients can be obtained, I will discuss it. Anyway, this is the coefficient will be supplied by the fuzzy engineer based on the different rule. So, for the ith rule, so these are the coefficient will be totally different, and this is a difficult job time to time for engineer to decide right value of this coefficient, because the output of a rule depends on the right choice of this coefficient value. Anyway, so if fuzzy, okay, we can depends on the wisdom of the fuzzy engineer, and let the fuzzy engineer suggest these are the coefficients for the ith rule, and therefore, for any input which satisfy this the rule, we can calculate the output. So, these are the basic things, and this is very difficult job for the engineer to decide this one. Once you decide it, then rest of the things is very straightforward and simple. Now, let us see how the rest of the part can be for the two rules, for the rules that we have discussed, which takes this form like. Now, according to this approach, it first calculate weight of a rule. For example, for the ith rule that we have discussed with the nth input, the weight, the ith weight can be calculated using this formula. This formula, it is like this: x 1 which is belongs to the fuzzy state A 1, taking its membership value, so mu A 1, and similarly for the another x 2 which is in the fuzzy state A 2, taking this membership value as mu A 2, and so on for the nth input, taking the fuzzy state A n and taking its membership value. So, it basically takes the product of the different membership values for all inputs belongs to the different fuzzy state. So, taking these are the values, we can calculate the weight of the ith rule. So, for whatever the rules are relevant, for each rule we will be able to calculate weight. Now, after the weight is calculated, the next step is to calculate the output value, it is called the y I. As I told you, so y I is associated with each rule, the y I is associated with each rule, and this is the y I value for the ith rule, and this is the weight for the ith rule that we have calculated in the last step, and taking these values for all the rules. Suppose there are k rules, and then taking the sum of product of all the w I into y I and divided by the sum of all weights, it will give you the final output, and that is the output. And you can say that this output y is basically the Cripps output, and this is the one difference from the Mamdani approach to the Takagi-Sugeno approach, where we need to calculate the fuzzy output first, and from the fuzzy output we have to calculate the Cripps output. But here directly from the fuzzy input as the rule, we can calculate the weights for each rule, and then the output value of this one, and then using this formula the final output which is in the Cripps value can be calculated. So, this way this is fast, because straight away we can avoid the fuzzification module there, and then we can directly come into the rule. Now, I can let us elaborate the Takagi-Sugeno approach with an example, so that we can understand. So, this is the method actually by which the Takagi-Sugeno approach calculates the output, and this is basically the mechanism where the fuzzy inference engine work. Whatever the rule base and then fuzzification and everything, that is the same as Mamdani approach. Now, let us consider as an illustration one example. So, let us consider is a two input system. Two inputs are denoted as I 1 and I 2. Let us consider this abstract input, and also consider that the two inputs I 1 and I 2 has the fuzzy linguistic, namely low, medium and high. That means, I 1 can be considered as a fuzzy state low, fuzzy state m or fuzzy state high, with the different values of the membership for the different values of I 1. Similarly, the other input I 2 has the three fuzzy linguistic again, they are called near denoted as NR, and far denoted as FR, and very far denoted as VF. So, there are three linguistics for the first input, and then three linguistic state or fuzzy state for the second input. Now, again if we follow the rule based matrix for this, and you can understand the rule based matrix has how many rules? Total 9 rules. So, if this is the L, M and R, it is so rule based system, it is like this. So, L, M and H. So, the 3 input for I 1, these are the I 1 and another 3 input for I 2. So, this is the I 2 and has NR, FR and then VF. Now, here in this rule it is basically, so there are 9 rules. So, rule 1 the Y 1 output, Y 2 and Y 3. Similarly, Y 4, Y 5, Y 6, Y 7, Y 8 and Y 9. Now, in the Mamdani approach we have observed that all the rules values here in terms of fuzzy linguistic, whereas in the Takagi-Sugeno approach all the rule values in terms of mathematical representation by which the Y 1, Y 2, Y 3 all these things can be calculated. So, if there is a rule, if I 1 is L and I 2 is NR, then the output Y 1 will be calculated using some mathematical notation. Now, for this again example, see what is the mathematical notation that we can consider out of these 9 rules, it is expressed here. Now, before going to this again let us consider the fuzzy linguistic state for 3 fuzzy states. So, far the I 1 input is concerned, which are denoted as L, M and H is shown here. So, it is the fuzzy state for the L, M and H. The fuzzy membership function it is like this, for L it is like this and for H it is like this. So, these are the fuzzy state defined for the I 1 and the input of I 1 is in the range 0 to 15 as it is mentioned here. Now, similarly, for the other input I 2 the range of values that is in 0.0 to 3.0 and above, and the fuzzy state that we have considered here it is shown here. For NR it is look like this, for FR it is like this the membership function and for VF the membership function is like this. Okay. So, this is the fuzzy state for the 2 inputs I 1 and I 2. Mu I 1 is the membership values for the different fuzzy state belongs to the input I 1 and mu I 2 is the membership values for the different fuzzy state belongs to the different input as I 2. Now, so this is the fuzzification module that is here, or it is basically the fuzzy design is there. That means, all the inputs should be represented in the form of a fuzzy linguistic, and we have discussed the 3 different fuzzy linguistic related to this illustration. Now, having this the fuzzy linguistics there, now we have to calculate for a particular instant, that means for a particular values of I 1 and for a particular values of I 2 at any moment, how the fuzzy input can Krips input can be converted to fuzzy input. It is basically the same method that we have discussed there and we can follow it. Now, here in this slide, say suppose each fuzzy rule that is denoted here in this expression. As I told you, again the same thing I can write it. So, it is basically Y 1, Y 2, Y 3, right, Y 4, Y 5, Y 6, Y 7, Y 8 and Y 9, 9 rules are there. For each rule that can be discussed in terms of the input value I 1 and I 2, and suppose we assume these are the what is called the mathematical representation of output values. Now, if we see, so this is the input I 1 and I 2 and then these are the coefficient. Now, all these coefficient needs to be decided by the designer. So, it is basically there are basically how many coefficients are there L, M and H. If we consider one coefficient A 1 and A 2, A 3 for this, similarly here NR, then FR and VF, then we can consider B 1, B 2, B 3. So, there. Now, so we have to decide the different values for this rule, if A 1 is 1, B 1 is this and this one. So, there are 9 different values to be considered here for j equals to 1, 2, 3 and some k equals to 0, 9 different values to be considered there. Now, for simplicity, suppose we consider the values a I like this one, a 1 for any rule I 1 is 1, a 2 I for any rule is 2, a 3 for any rule I 1 is 3. So, you have a simplified assumption and suppose it is decided like this one. So, alternatively I can say like y 1 this is equals to a 1 into I 1 plus say suppose b 1 into I 2, this is the one rule like. Similarly, y 2 there is another rule also can be considered likewise. So, all these expression that means for the output can be represented like this. Now, having this is the representation of a particular rule and corresponding to that particular rule basically the output value completes the rule base for the fuzzy system according to the Takagi-Sugeno approach. Now, let us consider a particular instant for a certain values of I 1 and I 2. We consider this is the input at any moment that I 1 is 6.0 and I 2 is 2.2. Now, given this is the input, we have to calculate the fuzzy output according to the Takagi-Sugeno approach. Let us see how it can be calculated. Now, again for this I 1 equals to 6.0 and I 2 2.2, we have to calculate the mu values of the elements that belongs to the two different fuzzy state here. So, I 1 is 6.0, so this basically this is say 6.0 and for the I 2 we have considered 2.2. So, it is a 2.2 right. So, if this is the then so this basically 6.0 belongs to the two fuzzy state M and as well as another fuzzy state L. So, I 1 is 6.0 belong to the fuzzy state M has the mu M I 1 value this one. So, it is basically mu M I 1 value this one. Similarly, the 6.0 the input I 1 belong to the fuzzy state L having this value. So, it is basically mu L I 1 is a value. Likewise, 2.2 has the two fuzzy state namely V f and then another is F r 2 1. So, this value and this value are to be calculated. So, these mu values can be calculated from this fuzzy description of the state the same way as it is followed there in the Mamdani approach using the principle of similarity of triangles. We can calculate it. So, these mu values will be obtained. Once these mu values are known to us, then we can calculate the output value easily. Now, here for an example we can calculate the mu value which is for the two input this one as this one mu L I 1, mu M this one and this one. So, these are the four different values that can be calculated from the fuzzy linguistic state description and using the similarity of principle that we have already discussed about in Mamdani approach. Now, so these values are known to us now. Now, we will use these values and then the output values for each can be calculated and so this is the method that can be calculated here. Now, here you can see again just like Mamdani approach there are 20 rules, here 9 rules. Now, out of the 9 rules we have to select those rules which are basically fireable. Fireable means those rules are relevant in the context of current input. Now, as we see for the I 1 equals to 6.0 and I 2 equals to 2.2 and when I 1 is 6.0 it belongs to the fuzzy state L and M. Similarly, when I 2 is 2.2 it belongs to the fuzzy state F r and V f. So, putting all these things together there are therefore 4 rules. The 4 rules are discussed here. So, if I 1 is L and I 2 is F r then it basically gives Y 1 one rule. Similarly, R 2 gives you Y 2 and this one gives you Y 3 and this gives you Y 4. So, the 4 rules and related to the 4 rules the 4 different output can be obtained. So, the next task is basically for each rule we have to calculate W 1. This is the W 1, that is the weighted value of the rule. For this rule also 2, for this rule 3 and for this rule 4. So, we have to calculate these are the values so far the output is concerned, and these are the values so far the rule's strength is concerned or weight is concerned. Once we have these values, then we can calculate W 1 and Y 1, where I equals to 1 to 4 is a numerator, and then the summation of W I equals to 1 to 4. So, this will give you the final output according to the Takagi-Sugeno approach. Now, let us see in the current context how the results can be obtained. For the two things are there, we have considered the different values of A 1 and B 1 in the context of this example. Now, here, so this basically shows the computation of the weights value. As I told you, it is a simple product of the membership values there. So, for the rule 1, the value that can be obtained is 0.6, for the rule the value that can be obtained 0.16 and like this one. So, these values can be obtained based on the different values of the membership values in the context of current input here or here. So, far the I 1 is concerned and these are the I 2 is concerned. So, W 1 can be calculated. Now, once the W 1 is known, then we will see how the Y 1 for each rule R 1 and R 2 can be calculated. So, here is the method by which the Y 1, that means output value, can be calculated. I told you that we will consider the different coefficients. For the rule 1, we take A 1 as 1 and B 1 as 2, and for others A 2 is 3, A 2 is 2 and B 2 is 3. So, these are the values of rule can be calculated like. So, for the different values, so here basically A 1 is 1 and B 1 is 2, and in this case B 2 is 3 and A 1 is 1. So, these are the basically the rule mathematical representation of the different rules are there, and then we can obtain the values of the outputs using this. This is basically the mathematical representation of the rule 1, and this is the mathematical representation of the rule 2 and mathematical rule 3 and rule 4. So, I have given this as an example, but actually these are the tricks by which this rule can be decided or defined in the system. And once these rules is defined according to the system, it is a straightforward to calculate in terms of the different value. For example, here I 1 is 6.0 and 2.2 and taking the B value is 2.1. So, this rule I 1 can be calculated this 10.4. So, this is the I 1 Y 1, the value is this one, and for the I 2 the value will be there, and I 3 the value will be there, and Y 4 the value will be there. So, 4 rules related to I 1 is 6.0 and I 2 is 2.2 can be calculated, their corresponding output values. We have calculated the weights of all these rules also. So, these values then can be used finally to calculate the final output. So, the final output is the formula according to the Takagi-Sugeno approach, that says that it is basically a product of the weighted output values. So, it is basically these are the sum of the product of weighted output values divided by the sum of the weights, and if we follow the calculation as we have obtained in the last calculations, then finally, the Y value that can be obtained as this one. So, the straightforward way from the rule base we can select the relevant rules, and from the relevant rules we can calculate the weights of each rules and then output values of each rules, and using this expression according to the Takagi-Sugeno approach we will be able to calculate the output value. And once the output value is known, then we can take a decision, and you can note that this is the output that we have obtained is crisp. As I told you, no need to follow any defuzzification method in this case straight away. Here basically straightaway, actually this is because straightaway for each rule we have taken the Cripps value, all these y 1, y 2 or all these are the Cripps value for each rule. That is why straightaway we can obtain the Cripps value as the final output. So, this is the method that is followed there in Takagi-Sugeno approach. And so, this is the way that the two controllers, the Mamdani approach and the Takagi-Sugeno approach can be designed, and two approaches have their own advantage as well as the disadvantage. And as I told you, so Mamdani approach is easy to interpret. Easy to interpret means rules are interpretable. On the other hand, the Takagi-Sugeno approach, the rules are difficult to interpret. So, less interpretability. Difficult to interpret because it is expressed in terms of some mathematical formula which needs some coefficients to be decided. Now, deciding the coefficient, it basically is a task for the fuzzy engineer or fuzzy designer. If the fuzzy designer can decide the coefficient correctly or accurately, then it will give the accurate result. So, accuracy of the fuzzy logic controller according to the Takagi-Sugeno approach solely depends on the performance or experience or prudence of the fuzzy designer. That is the only thing. Otherwise, fuzzy logic controller according to the Takagi-Sugeno approach is fast and more accurate compared to the Mamdani approach. So, it is up to the fuzzy designer which approach he wants to follow. If it is a critical application where accuracy and then the speed of the controller is very important, then they should follow Takagi-Sugeno approach. Otherwise, both the approach are equally applicable to design any fuzzy logic controller. So, this is the two controller we have discussed, and then using this the concept we can follow any fuzzy system can be designed from the fuzzy logic. So, this is end of the fuzzy logic discussion, and we will study about some case studies that will be given as some special problem for your practice. Okay, thank you.